My name is Larry Matta, and I'm a consultant here at Stress in the Midstream Group. My PhD is in aerospace engineering. I have a PE in mechanical, and I'm a certified fire and explosion investigator. And my fluids heavy background will be apparent in my presentation today. And if we meet sometime, you can ask me about the career path from aerospace to pipelines, which we usually prefer not to fly. Here at Stress, my pipeline work deals mostly with unusual loads on pipes like the spans we're going to talk about today, vibration issues due to things like compressor pulsations, water hammer and surge, surface loads, the effects of blasting on pipelines, and some other unusual things. But today we're here to talk about risks to pipeline spans, which come primarily through steady state stresses and vibration issues. And so let me start with a definition of a span. So when I say span, I'm going to mean any section of pipe that's not supported or that is only supported at its ends. It may have intermediate supports, but if you think about it, each section of a span then becomes its own individual span. If the supports are narrow, then adjacent spans are going to affect each other at the boundaries, and so we may need to consider interaction between them. And clearly, it's exposure that makes the spans vulnerable to threats that don't affect typical buried sections of a pipeline. So spans could be either intentional or unintentional. For intentional spans, sometimes designers take the shortest path across a ditch, which is a span. Unintended spans, on the other hand, are almost always caused by water. And failures of spans, they can lead to environmental problems. Since your spans are usually caused by water, it means that you can dump hydrocarbons into water. Of course, they're going to lead to expensive costs for repair and downtime. And failures at spans can also lead to a poor perception for the public of the pipeline industry in general. Failures can also lead to injuries, but it's uncommon for this type of failure. So mostly we're going to be concerned with environmental damage and economic problems. And in this presentation today, I'm going to be talking about some of the threats that affect spans and how we approach analyzing them. Let's look at a few examples to see what I'm talking about with spans. These pictures show an area between two hills that was filled in to make a road. And there's a culvert underneath that was supposed to divert any water, but it apparently washes out repeatedly and has become a problem. In this example, these were intentional spans, but erosion of the banks has made them longer than they originally were. And you can note the debris on the pipes shows that they are at least occasionally underwater. And these pipe spans, there's two pipes close together, a larger one and a smaller one, that were originally buried, but were exposed by erosion. And you can see that there's a support wire holding the pipe up. At least that's what it was intended to do, but it also collects debris, including the large log that's across it. And you can see upstream from the pipe, there's plenty of more logs that are waiting for their opportunity. And in these pictures, we had an unusually large flood event that caused fairly rapid erosion and exposed some sections of the pipe that aren't normally submerged. So you can see in the water, you can see some sections of the pipe, and it's not easy to find pictures of spans that are underwater because it's not usually easy to see them through the water. So when we look at pipes, we need to consider what loads we're going to look at it at which combinations. And the picture on this page is going to occur repeatedly in this presentation because it's helpful for a lot of the different topics. So the water or airflow over a span will give you drag forces and lift forces. The drag is almost always important for spans in flowing water. But it can also be important when your spans are exposed to high-speed winds. So you need to check your local design wind speeds. On the Gulf Coast, it can be 140-ish miles an hour. And at those speeds, you can get high drag loads even from air. Lift, at least for steady state, the average lift force should be 0 for a round pipe. But if there are anything like structures or you have a bundle of pipes or there are appurtenances, then you might need to consider lift loads as well. We've got gravity loads from the weight of the pipe and the weight of the contents, and also any coatings that might be on the pipe. And if the pipe's in water, you also need to consider buoyancy, because pipes in water may actually float instead of sag. We need to consider dynamic loads. Vortex-induced vibration we're going to be talking about a lot in this presentation. Turbulent buffeting can also occur, but we're not really going to be discussing it. But you could consider if you had a pipe become exposed in a river or just downstream of some rapids, that the turbulence of the water flow itself would be enough to cause some vibration in your piping. Flutter and gallop are also hydrodynamic issues that aren't really problems for round pipes, so you don't need to consider them unless you have something like ice accumulation or appurtenances, etc. Otherwise, you really don't need to worry about them, and we won't be talking about them today. There's also a potential for additional loads from impacts and debris accumulation, and we will get into some of those. So let's talk about what data you need to analyze the pipe. And this is just a list of data that's going to be useful for analyzing spans. And it's not uncommon for you not to have all of this information available. And what you do in those cases is you just make some assumptions. Usually you try to make some worst case assumptions that aren't too conservative. So for the pipeline itself, we need to know things like the wall size, the thickness, and the grade. You need to know where the pipe goes, so you need alignment sheets. We need pressures for calculating the stresses, the specific gravity of the contents for determining the weight, coating materials and thicknesses. If you have a pipe with, say, a 16th inch coating of polyurethane on it, that's not going to make any difference. But if I've got 4 inches of concrete, then I probably need to consider that in the analysis. Historic issues for both weld failures or corrosion issues are important, because you'd want to take that into account to derate the allowable stresses. And again, any weights or valves or anything like repairs near the span should probably be considered, and whether they need to be taken into account. As far as geometric data goes, we need to know what the length and shape of the span are. And for a detailed analysis, you're going to want to capture the profile not only of the span itself, but into the soil on either side of it, so that you can take into account the shape of the pipe where it's being supported. And you want to try to determine the cross-sectional shape of the pipe. If it's distorted at all, that could indicate that you've already got some problems, and it's going to be need to take account of it in the analysis. You also may want to consider doing NDT on exposed welds, which isn't geometric data, so I'm not quite sure why it ended up there, but that's where I put it. Soil properties, to get the boundary conditions correct, you need to know how the soil is supporting the pipe. So accurate soil properties are important, and you may want to consider geotechnical analysis in order to get those properties. And if the span is underwater, the velocity of the water is very important. And the problem is that the velocity of the water right now is useful information, but it's not going to help you predict your worst case scenarios. So what you need to do is predict the velocity of the water at various flood return periods, like 10 years or 50 years or 100 years, based on what risk factor you're willing to take. And that way you can get a velocity for a worst case scenario. Also, you want to look at scour profiles that would be associated with the flooding. The scour may cause a span where you don't already have one, or it may extend the length of a span that already exists. And potential for bank erosion and channel migration is the same concern. So when we're doing a static loading analysis, we want to look at a number of different things. So first we want to start with getting the gravity effect, which is basically the weight. So we need the weight of the pipe, its contents, its coatings, any swamp weights or anything like that that are added onto it. You also need to calculate the buoyancy. In air, the buoyancy is going to be so small that you can neglect it, but in water, it's always going to be important. The steady drag load, which is almost always important in flowing water and may be important in air, like we said before, if your design speeds are high for your air. Lift, again, it's going to be net zero in the steady case for round pipe, but it may be important if you have bundles or structures or anything else attached to the pipe that could cause the flow to prefer one direction or another. So let's talk about the methods that we use to calculate the steady loads. And basically it breaks down into analytical calculations or finite element analysis. Analytical calculations are based on equations, and they can usually be programmed into a spreadsheet or a simple application. And those allow for many spans to be assessed quickly with a minimum amount of data required. Now, this type of calculation is often conservative. In fact, it's often over-conservative. And the problem is that it's over-conservative until it's not conservative. And you don't really know when you have a non-conservative calculation. But if you have a non-conservative calculation, it's usually because you overstepped the limits of your assumptions. With a finite element analysis, on the other hand, we can get detailed assessments that account for things in like tension and other stresses. The FEA can give you a good representation of the soil boundary conditions as long as you have accurate knowledge of what your soil properties are. And you can also model different end conditions like supports and things like that. In the analytical calculations, we typically use beam theory to estimate the stresses due to the bending, and it's applicable to small deflections. And what I mean by that is that it's they're very accurate at small deflections, but the error increases with load and with deflection. So when is your deflection not small? Well, that depends on what your error tolerance is. Basically what we're assuming is that the pipes are straight and uniform over the length of the span. So we're assuming that the pipe is approximately horizontal and that it doesn't have any bends or branches or anything like that in the area of the span, including into the soil on either side for some distance away. If drag loads are important, then you've got gravity and buoyancy acting in a vertical plane, and the drag loads are happening in a horizontal plane. So it's perpendicular to the gravity loads. If the drag loads are uniform along the span and the weight of the pipe is also uniform along the span, then combining the two still gives you a 2D problem. It just gives it in a direction that's not quite vertical. Do you need to keep the analysis 2D for an assessment? No, you can still use beam models for 3D analysis, but when you reach a certain level of complexity, it's often just easier to switch to an FEA analysis. And if you do need to include specific details for an individual span, you've pretty much lost any benefit of an analytical method anyway. Okay, so once we know the bending stresses, how do we account for other stresses? And here's my figure again showing that the bending stresses are due to the loads in the figure. But if we have internal pressure or possibly stresses from thermal expansion or anything else that we need to calculate, we can do those independently and then add them to the bending stresses. As long as we're in the linear elastic range, and the bending, the beam bending equations are really only applicable to the elastic range anyway. So if we're in that range, then everything can just be added together. If we violate any of these assumptions, for example, we have bends or non-uniform drag loads, or say, for example, that you're using a strain-based design and you know you're going to have a little bit of, or allow for a little bit of plastic deformation, then you should just switch to an FEA model. Now, I put this slide in to compare an analytical model with FEA for a rigidly supported beam. So the beam model is the green dotted line, and you can see that it matches up with the FEA for when the pipe is allowed to slide in the supports. But this really doesn't give an example of what the supports look like for a real pipe. In that case, we're going to have tension in the pipe as well. So for the non-sliding FEA case, the pipe is rigidly attached at both ends, and in order to sag, it has to actually extend in length. It turns out that the non-sliding case has smaller deflection and overall stresses, even though it does include some tension in the pipe. So this just gives you an idea of where some of the over-conservatism can come from using the analytical models. Okay. Now let's talk about dynamic fluid loads, and really all we're going to talk about today are the vortex-induced vibration. So I'm going to hit the points on this slide pretty quickly and then give you more details as we go along. So when I'm done with this slide, if you're scratching your head a bit, don't worry, we're going to do a little deeper explanation. But for a wide range of flow conditions, flow past a circular cylinder like a pipe causes vortices to be shed from alternating sides of the cylinder. So if the flow is horizontal, then your pipe is going to shed vortices from the top and bottom. And these periodic vortices cause the wake to flap up and down and results in oscillating forces on the pipe. If the vortex shedding occurs near a natural frequency of the pipe, you'll get large amplitude response. And the large amplitude response of the pipe feeds back into the vortex shedding and causes larger amplitude vortices to be shed. So we basically end up with a feedback loop and a limit cycle oscillation, and the result is what we call vortex-induced vibration. Okay, so now I'm going to give a little better explanation of all of the stuff on this slide. So the colors in this chart represent the pressures calculated for a cylinder in a steady flow at an instant in time. So I've got flow from the left side of the page to the right side of the page. And you can see that as the flow goes past the cylinder, the wake starts to flap back and forth behind the cylinder, and that flapping back and forth of the wake causes oscillating forces on the pipe. So if we look at those oscillating forces, I've plotted those versus time here. The average drag load isn't zero, so it's got an average of 1 on this chart, whereas the lift does have an average of 0, so it's below the drag load. So what happens is as the vortices shed from the alternating from the top and bottom of the pipe, you get first on the lift curve, you'll get lift in the vertical direction, so it'll go in the upwards direction. And then when a vortex sheds from the other side of the pipe, you'll get lift in the down direction. And so you go back and forth getting an up and down lift force on the pipe. But the drag doesn't care if the vortex is being shed from the bottom or the top of the pipe. It just cares that a vortex is being shed. So what happens for it is that each time a vortex sheds, you get a little bit of an increase in drag and a little bit of a decrease in drag. The result is that the streamwise force oscillates at twice the frequency of the cross-flow force. So the drag oscillates at twice the lift oscillation speed. And also, I've graphed in this figure that the lift oscillation is significantly bigger than the drag oscillation, and that's true, and we'll get into that a little bit. So we define 2 directions of VIV. We've got inline and crossflow. So inline is in the direction of the flow, and then crossflow is, of course, perpendicular to that. The VIV has amplitude limits that are determined by the physics of the problem. And that physics is beyond the scope of this presentation, so I'm going to leave it as homework to the listeners. But the result is that the inline oscillations are limited to about 0.2 diameters, and the crossflow is limited to about 1.3 diameters. So in the direction of the flow, the pipe can only move with a peak-to-peak amplitude of about 0.4 diameters. But the crossflow can move about 2.6 diameters, which can be a significant amount of bending and can give relatively high stresses in the pipe. Okay, so vortex shedding occurs over a wide range of velocities. So from virtually stopped flow to very high rates of flow, the pipe will always want to shed vortices. And the frequency of that vortex shedding is roughly linear with the flow velocity. On the other hand, the pipe only has large amplitude response to the vortex shedding when the frequency of the vortex shedding is close to a natural frequency of the pipe. And that's when resonance occurs and we get large amplitudes of VIV. So what this picture is showing is mode shapes for the pipe. Some of them are completely irrelevant because having a free end on your pipe makes for a very useless pipeline. But if we look at the hinged and the fixed cases, it shows mode shapes that are applicable to pipeline spans. And as you move from left to right in those rows, you can see that you increase the number of mode. As the mode number increases, the corresponding frequency also increases. But the frequency that corresponds to these mode shapes is when the vortex shedding frequency matches those is when we end up with problems. So why are we worried about vortex-induced vibration? The bending back and forth of the pipe causes cyclic stresses. Those cyclic stresses can be very high if the amplitude of the VIV is large, and that can cause rapid fatigue damage, especially to welds, girth welds, and it can potentially lead to rapid failure. And if you think about it, if we're bending back and forth maybe once a second, and the amplitudes of the stress oscillation are not small, you accumulate fatigue cycles pretty quickly. And by pretty quickly, it can be a matter of weeks or days, or it can even be hours before you get failure if you get into a large amplitude VIV. Also, flexural vibrations, pipe bending, can cause significant damage to brittle coatings. If you have concrete on a pipe and you start flexing it back and forth, the concrete's just not going to last very long. We calculate the response of the VIV by a couple different methods, one of which is using response correlations. There's also a more complex force-based method where you actually calculate the lift and use it, apply it to the spring of the pipe to calculate the motion based on fluctuating hydrodynamic forces. And you can use either one of these methods. In some cases, one is more accurate than the other, but a lot of times your unknowns are so high that accuracy is questionable in the first place. So you're just looking for ballpark. And at high flow velocities, the limit length of the span based on VIV can be pretty short, and so often the onset of VIV is more important in determining the allowable span length for a pipe in flowing liquid than the steady state loads. Okay, this shows an example of a response correlation, and here's my only equation in this presentation, and it's fairly simple. So the reduced velocity is determined from the free stream velocity u divided by the natural frequency of the pipe and the diameter of the pipe. And the frequency of the pipe is determined by things like the mass of the pipe and the length of the pipe. So from the reduced velocity, you can find a maximum amplitude of the VIV for the pipe span. So if I have a reduced velocity of say 4, then I get a VIV amplitude of 0.4, and I can then take that amplitude and apply it to the mode shape of the pipe and calculate the dynamic bending stresses. And if I calculate the dynamic bending stresses, then I can use those to estimate a fatigue life. And you can also work backwards if you want to. If you have a cyclic stress that you consider to be an endurance limit, you can work backwards for the same way and come up with what your reduced velocity needs to be in order to avoid fatigue failure. Often we use a conservative approach, which we pick the onset velocity for VIV and try to stay below that. So if I'm concerned with cross flow velocity, then I could pick 2 as a reduced velocity, or maybe a little bit above that, and give myself a little extra latitude. And then we try to stay below that reduced velocity. If you know your flow velocity, and for your certain situation with your pipe and the length of the pipe, you're above that reduced velocity, that means that you need to change your natural frequencies by ways of, for instance, limiting the span length or stiffening the pipe some way. Now here's an example showing the onset of cross-flow VIV. On this graph, I plotted the flow velocity versus span length for the onset of cross-flow VIV for some pipe and a number of boundary conditions. So on here, I put pin-pinned, pin-fixed, and fixed-fixed boundary conditions. Fixed is usually not conservative for a soil supported pipe because the soil does have some give to it. Pinned is usually the other direction. It's overly conservative because the soil doesn't allow the pipe to flex that much. Pinned fixed is completely non-physical because it doesn't make any sense for a pipeline. But because it falls halfway between pinned and fixed, some operators will use that as their standard, as just a way of getting an average value between the two. This also shows some boundary conditions based on DNV RPF 105, which is for subsea pipelines that are laying on the sea floor. So it's somewhat applicable to buried pipelines that happen to have a span. But what's important from this particular graph is that the span length, allowable span length, is strongly affected by the support conditions. And it shows how important it can be to get accurate input conditions and possibly even to do testing to determine your natural frequencies if that's possible in your situation. Okay, let's do a brief case study on vortex-induced vibrations. So for this case, I've got a pipeline crossing that has river weights attached approximately every 10 feet to the pipe. And scour predictions were performed that indicated that some sections of the pipeline might become free spanning. The question then is, how do the weights affect the VIV? Does it make it better? Does it make it worse? So to investigate that, we did a modal analysis for a large number of span lengths using finite element analysis. In this case, we used Orcaflex. To calculate the natural frequencies with and without the suspended weights on the pipe. And we also calculated the natural frequencies using beam theory and analytical methods. In the analytical method, we distributed the weights into the weight of the pipe. So there was no point loads, it was just distributed along the pipe. And the theoretical calculation doesn't take into account any added stiffness from the weights. On the other hand, the FE model, we actually applied the weights in the model, and so the individual locations of the weights was calculated, and the stiffness effect of the weights themselves on the pipe was taken into account. So if we look at the analytical method, what we see is that the weight lowered the natural frequency of the pipe. And this is expected because the stiffness of the pipe didn't change, but we added mass to it. So from a mass spring damper system, we increased the mass and we lowered the natural frequency of the pipe. On the other hand, with the Orcaflex model, what we found was that in this case, at least, that the added stiffness from the weights themselves countered the added mass from the weights, and the natural frequencies ended up virtually unchanged. So what we ended up doing was using the analytical calculations because they provided a little bit of extra conservatism. So in this case, I've graphed the maximum span length allowable versus current speed for both the bare pipe and the pipe with weights. And the green line now provides a conservative warning line basically for the span lengths and the current speed. So if you're operating at a condition where your span length and your current speed come below the green line, you don't have to worry about VIV. Anything above that, and you need to consider the possibility that VIV is occurring. All right, let's shift over to debris impact. Debris impact is something that's really difficult to take into account because it's hard to predict what your debris impact is going to look like. You've got various sizes, weights, and locations, and none of that is easily predictable. One thing we can do is group them into 3 different types of loading and how to analyze those. So we can either have accumulations of debris that catch along the pipe and increase its drag, so like weeds being caught along the pipe. And these are, if they're local, then you can consider them a point load, or they can be distributed across the pipe and add a distributed increase in drag, and that can be added into the models. There's also a potential for high energy impacts, and what these do is they bend the pipe and they can bend it beyond its allowable limits, and we use energy methods to investigate these. And then third, there's localized impacts like a rock hitting your pipe that can cause denting or gouging of the pipe, and possibly damage of the coating that would allow for corrosion. And these localized impacts require a fairly detailed analysis because they simply can't be analyzed using beam models or something simple like that. And also the debris impact is usually only something that we're concerned with in submerged pipe. I can imagine that if you're in a hurricane or something that maybe you have to worry about debris impact from wind, but you probably have bigger problems. Here's an example of some debris accumulation. I don't know whether you want to consider the person standing on the pipe to be debris accumulation, but interesting in this case was that they installed a cable support to try to stop the pipe from bending under steady load. But what happened here instead is that the cable itself collects debris, and you can see that way up at the cross connection of the cables, there's debris there as well, indicating that even the cable was underwater at some point. These represent high energy impacts. It's really unlikely that anybody's going to design for a truck hitting their pipe. But if something like this floated downriver and bumped into the pipe, then that could definitely cause some damage. Ice impacts and accumulation. You can have an iceberg that bumps into a pipe that would cause either a localized impact or a high energy impact. But the other issue with ice is that as it builds up across a waterway, it can attach to the pipe and cause unusual stress loading that's hard to predict. Okay, so here's a case study of a high energy impact analysis. And in this case, it was a 10-inch nominal liquid pipeline with an operating pressure of about 1,300 PSI. It's not really important to the case study. If you look at the graph, the dashed line, I don't know what color I would call that, but it represents the ground. The red line represents the pipeline, and the blue dashed line represents the water. So in this case, we assumed that a log floating downstream that weighed about 500 pounds was our impactor. And so it's going to bump into the pipe, and we picked that spot shown as the impact location as to where to test it. So the log has a kinetic energy based on its mass and velocity, and we use that to determine the damage that it causes to the pipe. So by using a finite element model, we applied a force at the location of the impact, and by increasing that force, we can find the force displacement curve of the pipeline with respect to a load at that location. Then if we integrate that curve, we get the energy that's required to displace the pipe that much. So basically that's a potential energy of the spring that you're displacing with the impactor. If we set that potential energy of the spring equal to the kinetic energy of the log, then we find a point that that the log will impart its energy to the pipe. So in this case, what that shows is that we get a displacement from the log of about 4.8 inches. And then you take that 4.8 inch displacement and impose it to the pipe model, and you can calculate the stresses along the pipe from that. And what we got in this case is that the von Mises stresses and the longitudinal stresses both exceeded their allowables, indicating that in this scenario where a 500-pound log would impact at that location, that it would result in at least plastic deformation of the pipe, if not severe damage to it. So I threw a lot of stuff at you fairly quickly, but we can get some takeaways. First is that there's a number of scenarios that need to be considered in evaluating the loads and threats on pipe spans. We can use relatively simple analytical methods to screen for spans that require a more detailed analysis. The more data that you know about the pipeline, the soil, the environment, the more accurate your results are going to be. There are a number of threats where it can be difficult to predict what's going to happen, so it makes it very difficult to do an analysis, such as debris impact or ice on the pipeline. And a lot of the choices in which cases and the level of detail that you're going to do is determined by the risk tolerance. To get the risks as low as reasonably possible requires that someone in the chain decide what counts as reasonable risk. And so that includes choosing what scenarios need to be looked at. And I'd like to thank you for listening, and we'll take questions.